Welcome to Spatial Systems 101. Today we're diving into the world of spatial coordinate systems, the invisible grids that help us describe positions and movements in three-dimensional space. Whether you're working in biomechanics, robotics, or assistive technology, understanding these systems is crucial. Imagine trying to tell a robot arm exactly where to move or describing the precise angle of a knee joint. Coordinate systems make this possible. In this video, we'll explore the most common systems: Cartesian, polar, angular, and special reference systems used in robotics and rehabilitation. By the end, you'll see how these frameworks help us map, measure, and control movement with accuracy and clarity. Let's get started by looking at the basics of the Cartesian coordinate system. First up is the Cartesian coordinate system, the classic X, Y, Z grid you've seen in math and physics. Picture a 3D map where every point is defined by its distance along three straight axes: left, right, forward, backward, and up, down. This system is perfect for pinpointing exact positions, like telling a robotic arm where to reach in space. Next, we have the polar or angular system, which uses a radius and an angle instead of straight line. In 2D, it's just distance and angle. In 3D, it becomes spherical coordinates. This is especially useful for describing rotations like the bending of a knee or the swing of a robotic arm. Both systems are foundational, but each shines in different scenarios: Cartesian for fixed positions, polar for rotational movements. Beyond the basics, robotics and assistive technologies use specialized reference systems tailored to movement and interaction. The joint articular coordinate system attaches a mini coordinate grid to each joint, making it ideal for tracking human or robot limb motion. Think of how an exoskeleton matches its movement to your elbow. The End-effector system focuses on the robot's hand or tool, allowing precise control for tasks like feeding or grasping. Base or global system anchors everything to a fixed point, such as a wheelchair frame, ensuring all movements are measured consistently. Finally, sensor-based or task-oriented systems define coordinates relative to objects or sensors, perfect for tasks like picking up a cup or tracking motion in rehabilitation. Each system has its strengths, and together they enable smarter, safer, and more intuitive robotic assistance. Wrap up, let's compare these systems. Cartesian coordinates are like a 3D map, great for fixed, precise positions. Polar or angular systems excel at describing rotations and joint movements. Joint coordinate systems stick to each joint, perfect for matching human and robot motion. End-effector systems follow the robot's hand or tool, while base systems anchor everything to home position. Sensor-based systems adapt to the task or object at hand. Rehabilitation and robotics, choosing the right system ensures accuracy, safety, and efficiency. Understanding these frameworks empowers you to design better devices and smarter solutions for real-world challenges. Thanks for watching Spatial Systems 101. Now you're ready to map motion in any dimension.